Okay, so let's talk about organic chemistry. Initially, I thought we were going to conclude with nuclear, but turns out we're going to conclude with organic. And so, organic chemistry, it's interesting because we have this, huge periodic table of all these different elements. And one could think, oh, we could have a chemistry class based on each element, right? Because really, organic chemistry is the study of carbon, right? Carbon, organic materials, or I should say, carbon, hydrogen, and oxygen. But carbon is at the center of organic chemistry, right? It's the study of really all the different formations that carbon can get in these organic matter. And carbon is really interesting because it's abundant in us, is abundant in living organisms. So that's, in life as we know it. So we have a whole class just devoted to carbon, just devoted to studying organic matter. It might even be, it feels like it's the heart of chemistry. I was going to say it might even be the most important chemistry, but I don't like the idea of oh, something's more important, right? Because it's really about your interests and it's all important because it all exists, right? It all has an importance. But when I think of organic chemistry, it feels like it's the heart of chemistry. So consider that perspective as you are, from those of you that are going to journey into organic chemistry. Maybe center that perspective over the perspective that people often share, which is how difficult it is, and that's the class where a lot of people change their majors. I don't know why we highlight those things, but perhaps it should be highlighted because it is common. It is common. But I think it's unfortunate that it is that way, especially with me having this view or this insight that it may be the heart of chemistry. So that kind of sucks that it's the most challenging in the sense of the class that most students struggle through. I don't hear a lot of students say, "Oh my God, I loved organic chemistry." And if they do, they're probably the organic chemist, right? But it's like, what about a person that's a biologist? Can they grow to love organic chemistry? And this exists. So just keep that in mind as you are journeying into it. You get to shape the experience. Everybody has their experience and they're going to say this is what you can expect. And you can take all of that into account. But consider that it's the heart of chemistry. See if how that feels. All right. So we're going to start with alkanes. So alkanes are compounds that contain only carbon and hydrogen atoms. You'll also hear the term saturated hydrocarbons because the carbons are fully saturated with hydrogens because each carbon has an sp3 hybrid orbital. So here are some examples of alkanes. The simplest one, methane. We've got ethane, right, with two carbons connected. And then we've got pentane with five saturated carbons connected. So we've got the 2D line structure shown here. And these are 3D structures here, ball and stick, and then these spherical models here. So when we're drawing organic structures, there's three different ways that we draw them. One is the expanded structure, where we explicitly show every single atom and its connectivity, but we explicitly write what the atom is, right? So it's this carbon connected to three hydrogens connected to another carbon, and it's explicitly written. The condensed structure is not to write or show the carbon-hydrogen connectivities and to instead write things like CH, CH2, or CH3, right? Which is understood to be, this is a carbon that's connected to 3 hydrogens. So that's the condensed structure. Then we have the skeletal structure, which doesn't explicitly show any of the carbon or hydrogen atoms. It just only shows the connectivity, just shows the connectivity. And we know that every vertice is a carbon. Every vertice is a carbon. And the hydrogens are just understood to be there, right? Like literally every vertice or vertice, you get what I'm saying. Every point where we have a connection is a carbon. So we've got a carbon here, carbon there, carbon there, carbon there, carbon, 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 right? This is actually the same structure, just drawn in 3 different ways. But we know at these endpoints that this is a carbon that's connected to 3 hydrogens, right? So 3 different ways that we draw organic structures. And I would say all 3 ways are important, clearly, to know. But what you might see in common as you go deeper into organic chemistry and start looking at like reactions, that we will work more with the skeletal structures or condensed structure. And that's just because when you're drawing reactions, who wants to draw every single atom? It may be helpful to do that though, but we just start shorthanding because we get lazy. No, I'm kidding. It's a way to be more efficient. All right. So let's practice. Take this condensed structure here and write the skeletal structure. So pause this and draw it. All right. So this is what we should get. Right? We have this like little T formation here with all those carbons. And then we've got these 2 branching points here. So that's our skeletal structure. So for practice, take carbon hydrogen structures and go back and forth, go back and forth. And this might seem like, oh, that's a waste of time. I don't need to do that. I get it. By looking at this video, this makes sense. Here's why you want to practice it, because when you start doing reactions and drawing a ton of skeletal structures, it can be easy to like make little mistakes or forget things. So this is why right now it would make sense to just take several different structures and draw the skeletal structure. Look at several skeletal structures and then go back and write the condensed structure, right? So go back and forth, back and forth, go back and forth. Something like Quizlet might be a good tool to look at. Also in the textbook, there's some practice problems to do that as well. All right, so properties of alkanes. Non-cyclic alkanes, they have this general formula where however many number of carbons there are, which is represented by this sub N, we know how many hydrogens it's going to be. It's always going to be based on this formula. 2 times the number of carbons plus 2, always. So structural isomers are where alkanes, they have the same formula, but they can basically be connected differently. They can be connected differently or have a different structure, but the overall molecular formula is the same. So it has the same number of carbons, same number of hydrogens in the structure. So we could have this linear chain of carbons connected, or we could have a chain of 3 and then move one of these carbons to connect to this middle carbon here. So these are called structural isomers. Some other, so you don't need to memorize anything here, but just this is more about just seeing what we've experimentally been able to identify, right? This is the kind of data you'd collect to understand alkanes. You'd want to know, right, what's its melting point? What's its boiling point? What's its phase at standard temperature and pressure? What are the number, so we can actually determine the structure of molecules, right? There's experimental methods like NMR, mass spectrometry, where we can identify the structure of, I don't think we do the structure with mass spec. So fact check me on that. NMR, we can identify the structure. So we can see, we know there are structural isomers because we saw molecules where it was like it had the same molecular formula, but we noticed two different structures, right? So these are the types of data that you'd collect to understand these organic molecules. Let's see, greater number of atoms will lead to stronger intermolecular attractions, right? And that makes sense. There's more atoms in that molecule, so there's going to be more attraction, or they're engaging in some way. And also, each alkane is going to have different properties, different physical properties, right? So this is why we've been able to name these different alkanes, because they had different properties. They behave differently. All right, so this is literally the same slide that I just had before I had reformatted. So, general formula for alkanes, right? An example of structural isomers. Make sure you understand what we mean by, and this is why we call it a structural isomer, is because the structures are different. All right. So here's the thing with naming. It's like you need to know the name of things to be able to understand its properties and how it behaves and engages in chemical reactions. So that's why there's this arduous process of naming molecules. I am not going to test you on naming. That's something you will get tested on as journey into organic chemistry. What's more important here I want you to go through this and have seen how we name them so you can start being connected to the names of organic molecules, right? So just go through the steps, practice but don't stress over. Don't be overwhelmed by it. Oh my God, don't think, oh my God, I gotta memorize these 6 steps. Just read through the steps and then see and just go through some examples. So you're gonna find the longest carbon chain. So I'm just gonna read the steps and then we're gonna go through an example, right? So for some of you, if you're not like driving or doing something, um, I'm gonna read the steps and just maybe close your eyes and just listen to it in this moment. Don't you're gonna come back and maybe write it in your notes, but just for now, just like listen to it. So first we're gonna find the longest carbon chain. This is gonna determine the parent, or you might hear the word base name of the alkane. And then you're going to identify all the substituents. These are what we call alkyl groups, or functional groups that are coming off of that main chain. Then you're going to number the parent chain, start from the end closest to the first substituent, so the substituents get the lowest possible number. That'll make sense when we look at an example. So you're going to number the parent chain. Then you're going to assign a number to each substituent. So we're numbering so we can be able to identify where the substituents on the parent chain is. So you're going to write the number followed by the substituent name. You're going to use prefixes. The words are not coming right now, and it might be because it's mad late, right? So don't judge me for this. So you're going to use prefixes like di, tri, tetra, right, to correspond with two, if it's at the two position, three, four, etc. Then we're going to alphabetize the substituents and list them in alphabetical order. All right, let's just do an example. Oh, before we do an example, so open your eyes if your eyes were closed. And these are different alkyl groups. They are the substituents or functional groups that can come off of that carbon chain. And we name each of them. So if it's just a CH3, that carbon is connected to the parent chain, that's an methyl group, right? If we have two carbons coming off the parent chain, that's an ethyl group, and so forth. So this is important to know because this is how we name the alkyl groups. Okay, so in this example, first we identify the longest carbon chain, which is, right, we could go 1, 2, 3 or 1, 2, 3, either direction here. The only reason we can go either direction is because we have a substituent or a functional group coming off the chain, which is a chloro group. It happens to sit dead in the middle. Now, if there was another carbon over here, then we would number it from left to right because that would result as its functional group chloro being numbered at the lowest possible number on the parent chain. So it's at the 2 position here. So we name this 2-chloro propane. Propane is the name of the parent chain. I feel like that rhymed. I hope you're picking up what I'm putting down. So there's 3 carbons, right? That name of that parent chain is propane. And then, but we first put the substituent in its location. So chloro, its address is basically at the 2 position of propane. So it's 2-chloropropane. All right. I'm going to move through these other examples a little quicker. So we've got this carbon chain with 2 substituents, 1 bromo, 1 chloro. Pause it to go through it a little slower if you need to, right? We number it from this direction because the bromo is at the first position. It's at the lower number, as opposed to if we numbered from this direction, our substituents would be at a higher number. So this is 1 bromo, 3 chlorohexane. Last example. So you might be like, whoa, this seems like a lot. Maybe not. It seemed overwhelming. And the reason is because this is drawn as the extended structure. So do you see why it can help to write it in the condensed structure or even the skeletal structure? Because it can be easier to sort of digest, right? So longest chain is here. We've got 6 carbons. Hexane is our parent name. We've got the substituent off of carbon number 3. And it's a ethyl group because there's 2 carbons here. So we've got 3 ethyl hexane. All right. We're going to pause there for alkanes. So the main thing, I want you to know what an alkane is, right? I want you to know why we call an alkane a saturated hydrocarbon, right? Know what the hybridization of carbons are in alkanes. And just briefly be familiar with how we name them. right? Because if you see propane or methane, it should just, its name. You should see a carbon with 4 hydrogens and just know that is methane. And if you don't, then stay here a little bit, right? Maybe go over more examples of naming alkanes if it's like, I have no idea what this is. Because we've been using these terminology, we've been naming them throughout Gen Chem, right? But now we're going deeper into, okay, let's take a step back and talk you through why it's named the way that it's named, because you're going to see new molecules and you need to have a way of being able to name it because you're going to see so many new molecules at a rapid pace when you go into organic chemistry. Whereas here, if you think about it, you saw a lot of molecules in this class, but we kind of repeated a lot of the same molecules, right? You saw acetic acid a lot. You saw hydrochloric acid, sodium hydroxide. There were a lot of molecules introduced, but there's going to be a lot more introduced in organic chemistry. And so you need to be able to quickly type them, name them. So that's why naming is important. All right. See you in the next video.